Hi everyone. As we continue our series of lectures on physical science, we're going to pick up almost where we left off with the heat and matter, and we're going to move into light. When we were talking about heat, excuse me, in the last lecture, we were taking a look at the fact that as something heats up, it will give off a certain frequency of light. That frequency of light is tied directly to its temperature. Well, something else that frequency of light will tie to is the color of light that is being produced. So let's take a look at what exactly is light, and what can we learn from it? So, atoms absorb energy, okay, and atoms will absorb energy and respond in a couple of different ways. They will move faster. And when it moves faster, if electrons absorb energy, they will move to a higher energy state. Those will, like when you are putting energy into an atom, its electrons are going to move faster, and so they're going to be excited. They're going to bounce up to a higher energy state. That is called excitation. Well, electrons can't stay at that excited state forever. They actually will drop back down. They don't stay there long, they will drop back down. And well, in order to drop back down, they have to release energy in order to do that. Well, when they release energy, they release that energy in the form of light photons as they go through what's called de-excitation. So going from one level from an excited level to a de-excited level, or their ground state, they release a photon of light. And so this is what we actually see when we see light. What we're watching when we see light is the result of electrons bouncing back and forth between an excited state and a de-excited state. And so that releases this electromagnetic wave. It releases a photon of energy in a certain wave. And so we get this electromagnetic energy that we call light. Now, some light we can actually see, and some light we can't see. If we think about all of the electromagnetic waves, we're only able to see a certain number of those that are in our visual spectrum. But there are others that we can't see, like radio waves. We can't see heat. We might see the results of heat, and if we have infrared glasses where we can see infrared, then we might be able to see heat. But we can't see things that are beyond the visual spectrum either, like X-rays or such like that. So when atoms absorb energy and then they give that energy back off, we get both an electrical field and a magnetic field, because that's what an electromagnetic wave is. And so what we end up with are two waves that are moving perpendicular to one another. And when they move perpendicular to one another, each one of the waves will start the other wave. So electromagnetic waves are actually self-propagating. They're just why they can go through space. Other waves need a medium to go through, but electromagnetic waves not so much. Let's think about what we see whenever we think about a wave. So frequency of a wave is the number of cycles of a wave that are occurring in 1 second. That's typically what we refer to as the frequency. So here's a diagram showing us an electromagnetic wave. Now let's just take a look here at the various parts of a wave. To start with, if we're looking at a wave, this high point here on the wave is called a crest. The low point in the wave is called a trough. If we measure the distance from crest to crest, or from trough to trough, we get the wavelength of that wave. So crest, trough, the wavelength is from crest to crest or from trough to trough. And if I'm timing how many of these waves go past me, each crest, if I count the number of crests that pass me in a certain amount of time, say for instance a second, then that's going to give me the frequency of the wave. So I've got wavelength and I've got frequency. Frequency is how many crests pass in a second. Wavelength is the distance from crest to crest. So if we think about the wavelength, wavelength and frequency, okay, light, since all light is traveling at the same speed, wavelength and frequency are going to be tied to one another. We can see this is the entire electromagnetic spectrum. We only see part of it here in the visible spectrum. This would be at frequencies that are too high for us to see. Up here, these are in frequencies that are too low for us to see. Now, if we take a look at just the visual spectrum, red is down here, and so this would red light carries much less energy because it is a lower frequency and it is a longer wavelength. Okay, low frequency, long wavelength. Violet has a very short wavelength and a very high frequency. Okay, so this carries more energy. Well, let's think about this wavelengths. Very long wavelengths to very short wavelengths. So the shorter the wavelength of the light, the lower the frequency. The higher the frequency. So long wavelengths equals low frequency. Well, that makes sense because if you have a long wavelength, then fewer crests are going to pass by in that same second. And if you have shorter wavelengths, like the violet down here, shorter wavelengths means that you're going to get more crests passing the same point in the same second. So that means you have a higher frequency. So long wavelength, low frequency, short wavelength, high frequency. And the frequency, the higher the frequency, the higher the energy level. So violet light has more energy than, say, red light. But, so what does this matter to us? Remember what I said a little bit ago is that you're going to have, whenever a light is produced, it's because electrons are bouncing to a higher energy level and then falling back down. So they're being excited and they're de-exciting. So you get light given off during that de-excitation. So depending on the wavelength of light that's given off during that de-excitation, that's going to make a difference in the color of light that is being given off, or the type of electromagnetic wave that you're going to get that's not necessarily in the visible light spectrum. So white light, the light that you see coming from the sun, is a mixture of all lights. You get the same kind of all colors, all wavelengths, and you get the same kind of light coming from an incandescent bulb. It is a mixture of lights, mixture of colors, and we see Roy G. Biv, which is red, orange, yellow, green, blue, indigo, and violet. And you can separate these with a prism. Notice that this is exactly the opposite from pigments. When we talk about light, white light is the presence of all colors. And then, of course, the absence of all colors would be darkness, no light. But in pigment, the presence of all colors is going to give you this dark, the black, and then, so colors are additive in pigment, and then you get something entirely, it's just the opposite of pigments and light here. So when we are talking about colors, white light can be separated into the different wavelengths with a prism. You see this when light is refracted through water. If you're spraying water, then light comes through and you get this rainbow effect. Well, what's always on the top of the rainbow? Red. Red is always on the top. That's a long wavelength of light. What's always at the bottom? That's your violet, because that's the shortest wavelengths of light. So when you separate light into the rainbow, you're always going to get this red, orange, yellow, green, blue, indigo, and violet all the way down from the longest wavelengths to the shortest wavelengths. index of refraction, this is the ratio of the speed of light in a vacuum to the speed of light in a particular material. So the index of refraction is going to it tells you how much light slows down as it goes from one medium to another. Okay, light will change speed as it goes from one medium to another, which is why we get a rainbow when light passes through water, or when light passes through a prism, because the light itself changes speed as it's going through a different medium. Okay. All right, so we've already talked about wavelength. The wavelength is the horizontal distance between successive wave crests or between successive troughs. So different wavelengths refract at different angles because they don't travel at the same speed, which is why we're getting this refraction. You're getting this rainbow effect when light goes through a prism, because the different wavelengths of light will bend slightly differently as it goes through the prism, and so that's why you end up with a rainbow. Violet refracts the most. That's why you get it on the bottom of the rainbow. And red refracts the least, which is why you get that at the top of the rainbow. So if we take a look at this refracting through a raindrop, okay, so as the light comes through, it's going to refract, and so you end up with the observer seeing this rainbow here. So light has wave properties in that it expands outward and it rebounds when it strikes a surface, and then sometimes it will pass through. As it passes through a different medium, that's when you get refraction, and then the light waves will also pass through one another. Light waves do not need a medium to travel. They travel through a vacuum, obviously, because light travels through space. Light will interact with matter. Light will definitely interact with matter, and it will depend on the smoothness of the surface, the nature of the material that's part of the surface, and then the angle of incidence, that is the angle that the light is coming in and hitting the surface. Possible interactions. What are our interactions? You could reflect. Think about a mirror. Okay, so when you shine light on a mirror, if you shine directly at the mirror, it's going to reflect right back at you. But if you change that angle, it's going to reflect off of the mirror and go off at different angles. So the shallower the angle, the more of an angle you get with the light that is reflecting off of the mirrored surface. The deeper the angle, or the bigger the angle, the less of an angle, the more acute the angle is going to be for the reflected light. So that's when light is bouncing off a surface. Okay, we see the moon because it is reflecting light from the sun. The moon doesn't create any light on its own. Light can also be refracted. Okay, that's when light changes speed going through a different medium. That's what creates rainbows. Okay, light can be diffracted. That is when a wave bends, or actually as it's going around something, not through it, but around something. That's diffraction. Light could be absorbed. There are some bodies that will can absorb light, and then other things will transmit light, depending on if it's opaque or if it's translucent. Something that is translucent will simply transmit light going through it. Something that some things will absorb light, like if you have like a shade, part of the light will get absorbed as it's going through. So if we think about shining a light through some sort of an object, okay, you may get some light that's reflected. Some light may be absorbed, in which case you don't see it anymore. This is a refraction, because as the light comes through, it is refracted. It changes speed, and then when it comes out the other side, we say that would be then transmitted light. So we have reflected light, we have refracted light, we have absorbed light, and we have transmitted light. Light interacting with matter, and like I said, when light can bend around things, or waves will bend around things. That's why you get ambient light. If somebody is behind a wall and shines a flashlight, if they're depending on the flashlight and whatnot, you're going to see ambient light coming around the wall, unless it's all walled in or something like that. That's diffraction. Okay, so light interacts with matter and is reflected, transmitted, diffracted, absorbed, and all combinations of these are possible. So materials, depending on the material, you might have a transparent material, which will only transmit light going through it. We have opaque materials, which don't allow any transmission of light, which would be like if you had curtains, like full blackout curtains in your house that will totally black out the light. That's an opaque. Or you could have things that are translucent that does allow some transmission of light through them. Like if you have shears hanging in your house, light will come through, but not as bright as if you were just outside. So that's translucent. Colors that we see result from selective wavelengths being colors that you see on something. Selective wavelengths being either reflected or absorbed. When you see something that is red, that means that all of the colors other than red have been absorbed, and the red wavelengths of light have been reflected, and so you actually see the red that is there. Refraction, whenever light crosses a boundary, and we've just talked about this, whenever light crosses a boundary changing from one substance to another, we will say that that light has been refracted. It's refracted because it changes speed. It changes speed as it goes into a different medium. You have absolutely experienced this when you look, if you're looking through one corner of an aquarium through to the other side of the aquarium. You have a very difficult time seeing all the way through because the light that you're looking at is coming in at a different angle, and so you don't actually see what it looks like you ought to see. Or if I took a pencil and stuck it down in a glass of water, then you see what looks like the pencil is broken. It looks like the pencil is bent, and that's because we're looking at it, and as the light goes from air into the water, it changes speed, so we have this refraction going on. So light bends from the normal as it moves from one medium to another. And again, that refraction is what creates the rainbow effect. So whenever light is moving from one medium to another, it changes speed, and as it bends away or from the normal, that's what we see as like either the bent pencil or something like that. So the magnitude of the refraction depends on the angle that the light strikes the surface and the ratio of the speed of light between the two surfaces, or between the two substances. Okay, like between water and air, there's a certain index of refraction, and that's what's going to cause that bending effect. Some glass will have a bigger index of refraction, which is why with aquariums you can't really see around the corner from one side of the aquarium to the other, because the light is bending so far away from the normal line of sight. So lenses, think about lenses like my glasses right here. Lenses make use of refraction in order to allow you to focus more, allows you to focus images. So you have concave lenses. Concave means that it's shaped like a cave, okay, so it's curved. So this would be a concave surface right here of my curved hand. We have a concave surface. So this is used to help correct vision. Convex, it's kind of like a magnifying glass. This is for like reading glasses, you could say. And that's when you have this surface right here. This is convex. So if I only have one curve, this side is concave, this side is convex. Okay. Converging lenses, also used in lenses. These are magnifiers, cameras, eyeglasses, telescopes. Those would all be using convex lenses. So here's a concave lens. Light rays hitting this side and they're bent outward. Here's a convex lens. Light hitting it straight and it converges on a particular point. And if you have, this would be called the focal point right here. And if you could see the image that's where it has come apart on this side, you would see that the image is actually inverted, which is the lens in your eye does this. So here are some study websites, things that you will need to know for the gaze, and there's your primer on light.